Welcome. Thanks for tuning in. This is Scaduto speaking. And let me start by thanking the organizers for inviting me to present this work. Everything here is joint work with Ali Daemi, and this is part 2 of a 4-part series on equivariant singular instanton homology. The goal of this talk is to tell you about some of the motivating ideas behind the constructions, and also to describe the types of algebraic invariants that come out of the theory. So let's get started. Let K be a knot in the 3-sphere with an orientation and a base point P. Then we have a preferred small meridian loop mu around this base point. From this data, we can define the representation space R of K to consist of representations from the knot group to SU2, which send that preferred meridian to the diagonal matrix I minus I. So this space has a circle action. You can conjugate any of those representations by a diagonal matrix in SU2, and you preserve that condition on the meridian. I should point out that the center of SU2, which is plus or minus the identity, acts trivially on everything here, so we always assume we've already modded out by it. So if you take the quotient of this representation space R of K by this circle action, you get the traceless SU2 character variety of the knot. So these spaces are real algebraic varieties, but in general they're not smooth. They might be highly singular. On the other hand, the circle action on R of K is quite nice. It's free everywhere except for a unique isolated fixed point. So we call this reducible because it corresponds to the reducible representation, and it's distinguished as being the only abelian representation in R of K. On occasion, we might want to throw out this reducible and only consider the character variety of irreducibles. There's a gauge-theoretic interpretation of the representation space R of K. Consider the space of SU2 connections on the knot complement satisfying the following conditions. First, if you take any meridian around your knot and shrink it, then the holonomy of a connection around that meridian should approach a traceless element of SU2. The second condition is that if you do this for the preferred meridian mu, then your holonomy is asymptotic to I minus I, not just any traceless element of SU2. If we mod out this space of connections by the appropriate gauge transformations, then we obtain the framed configuration space of singular SU2 connections. And it's the second condition which is the framing for the connection. So if we forget about that, we obtain the ordinary configuration space of singular SU2 connections. And there's a circle action on the framed configuration space such that the quotient is the ordinary configuration space. Now there's a Chern-Simons functional on the framed configuration space. Its values lie in R mod Z, and this functional is invariant with respect to the circle action, and it descends to the ordinary configuration space. I won't write down this functional. The important point I want to make here is that the representation space R of K is in bijection with the space of flat connections in the framed configuration space. And this is a circle equivariant bijection. These flat connections, in turn, can be identified with the critical set of the Chern-Simons functional. And again, if you quotient by this circle action, you get the character variety. Now the motivating idea is to do S1 equivariant Morse Floer theory for this Chern-Simons functional. In actuality, we might need to perturb the functional to achieve some version of transversality. What was once the character variety, after perturbation, becomes a finite set. I've written here alpha 1 to alpha n for for the irreducible critical points of this set, and theta for the reducible. Now this is downstairs after having modded out by the circle action. So upstairs, what was once R of k becomes, after perturbation, a disjoint union of circles, one for each alpha I, together with the reducible, which is still just a point. If we can do Morse theory in this setting, or more precisely Morse Floer theory, our chain complex should look something like the following. Its underlying abelian group should be the homology of the space R of k after perturbation. So here the z summand corresponds to the reducible critical point theta. As we're doing Floer theory, the grading turns out not to be in z, but in z mod 4 in this case. And the differential, which we call d tilde, involves certain singular instanton moduli spaces. I won't write this down, but you can look at the paper if you want more details. So you'll note that I indicated a map chi on this chain complex, and you should think of this as remembering the S1 equivariant structure. So note that downstairs we have these irreducible critical points alpha I, and upstairs there's an S1 orbit for each of them. So on the level of homology, each alpha I is contributing 2 generators, and the map chi pairs these off. Let's formalize the algebraic structure we see appearing here. Define an S complex to be the data of a freely generated chain complex, C tilde D tilde, along with an endomorphism chi of degree 1, such that the following hold. First, chi should square to 0 and be an anti-chain map. And second, there should be a distinguished sumend z in grading 0, such that the kernel of chi is equal to the image of chi plus this sumend. And you should think of this sumend as always corresponding to the reducible critical point. It turns out that any S complex is isomorphic to one of the following form. So here, C tilde has a decomposition just as on the previous slide. And here are the non-zero components of the differential D tilde. These components satisfy some relations to ensure that D tilde squares to 0. And the map chi maps C star to C star minus 1 isomorphically. In particular, you can see where the image and the kernel of chi are. Next, a morphism between two S complexes is a degree 0 chain map which respects the chi maps, and, very importantly for us, it maps the distinguished Z sumends isomorphically. So once we've chosen the right notion of morphism, it's then straightforward to define chain homotopies of S complexes, chain homotopy equivalences, and so on. And you can do most of the things you would want to do with S complexes. You can take tensor products. You can take duals. And you do most of these things in the exact way you would expect to. For example, to take the dual, you just take the duals of each part of the structure. Now I can state the following theorem. To a knot K, we construct a Z mod 4 graded S complex, which we call C tilde of K, and it's constructed using singular instanton Floer theory, motivated by the ideas described earlier. As usual in Floer theory, the construction depends on a few choices, like a metric and a perturbation. But the S complex we get is an invariant of the knot K up to chain homotopy equivalences of S complexes. A lot of these ideas are not new. So this construction is modeled on a similar construction, which can be found in Donaldson's book on Floer homology, which is done in the setting of ordinary SU2 gauge theory for integer homology 3 spheres. And a lot of the structure there was also developed by Freushoff. Also, I cannot overemphasize how many of the ideas and foundational work of Chern-Simons and Ravka in the setting of singular SU2 gauge theory are used in the construction. So now that we have this algebraic invariant C tilde of K associated to our knot, what can we do with it? Well, one thing we can do is just take its homology. And we can prove that if you do that, you recover Chern-Simons and Ravka's I natural of K. I'll say a few more words about that later. Another thing you can do with an S complex is take what we call its irreducible homology. So on the previous slides, when we decomposed C tilde and wrote it as C star plus C star minus 1 plus Z, the irreducible homology is just taking the homology of C star. Another way of saying that is to take the homology of the image of chi up to a grading shift. So we can define the irreducible instanton homology of a knot to be the irreducible homology of its S complex. We call it the irreducible homology because at the chain level it's generated by the irreducible character variety up to perturbation. This is a Z-mod 4-graded abelian group. It has the very nice property that it categorifies the signature, or half the signature, in the sense that if you take its Euler characteristic, then it's equal to 1/2 the signature. And this really follows from work of Chris Harold. I star of K is also important because it really is the direct analog of Floer's Z mod 8 graded instanton homology for integer homology 3 spheres. Another thing we can do with an S complex is define what we call its equivariant homology groups. So given our S complex, we can associate to it 3 chain complexes over the polynomial ring Z adjoint X, which we think of as dual to the cohomology of the classifying space of a circle. So the degree of X is -2. So here we define 3 chain complexes, C from, C2, and C bar, each with the differential as written here. And the notation here is inspired from similar notation in the setting of monopole Floer homology. Doing some algebra shows that the homology of the C bar complex is always pretty simple. It's isomorphic to a Laurent power series ring in the variable X inverse. And now we can define 3 equivariant singular instanton Floer groups, I from, I to, and I bar of a knot. So these are Z mod 4 graded abelian groups, which are modules over Z adjoint X. And in particular, the I bar theory is this Laurent power series ring. It follows algebraically from the constructions that we get some exact triangles for these groups. The first exact triangle relates the 3 equivariant theories, to, from, and bar. The second exact triangle relates the from theory to the homology of C tilde, which on the previous slide we identified with I natural. Now if you're familiar with Heegard-Floer theory, these algebraic structures may look familiar. It's a conjecture of Chern-Simons and Ravka that I natural of a knot is isomorphic to the hat version of knot Floer homology from Heegard-Floer theory. They make this conjecture of the complex numbers, perhaps just because they were working over the complex numbers in that paper. So you should think of the I from, I to, and I bar theories of a knot as counterparts of the minus, plus, and infinity versions of a knot from Heegard-Floer theory. I should also point out here that Jiankun Li defined another counterpart of HFK minus in the setting of instanton homology using sutured instanton homology. So it'd be interesting to determine the relationship between these theories. To summarize, We construct this S complex for a knot, and then from it we can algebraically extract a number of other invariants. For example, if we take the homology, we recover Kronheimer and Ravka's I natural. If we take the so-called irreducible homology, we get this interesting theory I star of k, which categorifies the knot signature. We can also construct these equivariant homology groups from the S complex, in which case we get this triad of ZX modules. And we can do more. So for example, we can take Froyshov invariants. I won't discuss that here, but you can see part 3 of this series for more on that. I'd like to say a few things about this isomorphism between the homology of our S complex and I natural. First, the isomorphism is not degree 0 mod 4. The degree is the signature mod 4. In some sense, this isn't so important and really comes down to a difference of conventions. Second, the isomorphism is not obvious from the constructions of the two theories. To prove it, we use a variant of the following theorem. So given two knots k and k prime, the S complex of their connected sum is chain homotopy equivalent as an S complex to the tensor product of the two S complexes of the knots. To say a bit more, in the construction of I natural, Kronheimer and Ravka take the connected sum of the knot k with a Hopf link, and they do gauge theory for a non-trivial bundle in this setup. This is different from our situation because in their situation there are no reducible connections. The variant of the theorem we then use to relate the two theories involves choosing k prime to be a Hopf link with a non-trivial bundle. So hopefully I've convinced you that the S complex we've constructed for a knot can be a very interesting algebraic invariant. Unfortunately, the invariant gamma from part 1 of this series isn't determined by the S complex that we've been talking about. In fact, we need extra structure, which we have so far omitted from the discussion. So let me start talking about what this extra structure is. The first point to make is that so far we've worked over the integers, and we're going to generalize that to the setting of local coefficients. A lot of this follows ideas of Kronheimer and Ravka. Recall that we have a Chern-Simons functional defined on a configuration space of singular SU2 connections for the knot. And this configuration space, B of k, is a quotient of a space of connections by some gauge group G. This gauge group G is homotopy equivalent to a space of maps from S3 to SU2, which send the knot K into the maximal torus U1 of SU2. For any such map G, we can associate two integers, K and L. K is the degree of the map G viewed as a map from the 3-sphere to itself, and L is the degree of the map G restricted to the knot K, viewed as a map from the circle to itself. So we can compute the fundamental group of the configuration space B of k. It's isomorphic to pi 0 of this gauge group G, which by the above construction is isomorphic to Z plus Z, associating to a map G the two integers k and L. Having identified pi 1 of B of k, we can then work with a local coefficient system, which we call delta, on the configuration space B of k. So we can do all of the constructions we described earlier with this local coefficient system. So we obtain an S complex, C tilde of k delta, which is a chain complex over the ring Z adjoin pi 1 of B of k, which is the Laurent polynomial ring in two variables. But wait, there's more. This is not the only structure that's required to define the gamma invariant. So there's a bigrading on this S complex, and this bigrading has values in Z cross R. You should think of the Z grading as a homological grading, which actually reduces to the Z mod 4 grading. And the interesting grading here is the real grading. So that's coming from values of the Chern-Simons functional. And the differential d tilde decreases this R grading. So this is a very important property, which is really coming from the fact that the energy of an instanton is non-negative. And I'll just end by saying that the invariant gamma k that was discussed in part 1 of this series comes from the S complex C tilde of k delta, equipped with this extra structure of the Z cross R bigrading and the filtration induced by the R grading. Well, that does it for this talk. Thanks very much for everyone's attention. All of the results discussed here are available in more detail in our preprint listed below, which is available on the archive. I should remark that unlike this talk, Part 1 and the next 2 parts of this series include some results which are not in this preprint, but those will appear in a preprint which should be in the archive soon.